So the question is, if a knot is fibered, the complement fibers of the circle with irreciprocal point being the cyclic surface for the knot, is there possibly a lower genus cyclic surface? And so,
so you're saying that there is that it's only fibered by the minimal genus surface?
well, there may be other minimal genus surfaces that are not fibers. But I mean, there are many different. You can. Minimal genus cyclic surfaces are not unique in the sense that there can be non-isotopic minimal genus surfaces. But I claim that if it is fibered, then the fiber cyclic surface is minimal genus.
Okay. So
but not all minimal genus cyclic surfaces.
Yeah, but that's still stronger than what the question was.
Your question was, is there an example?
Is it possible to fiber it with higher genus things?
No, I think I'm saying the contrapositive of that statement. I'm saying, so my claim is that if fibers, then for every vibration, the fiber equals minimal genus cyclic surface.
Okay, sure. But if it's not minimal genus, then it doesn't fiber.
And so, what I want to do is say that suppose the knot fibers, then you know precisely what the homology of the infinite cyclic cover is. Forget about mods, forget about the action of T on the gradient, right? So that let me see if I can construct this. So if K fibers, then that implies that, so I would take an x equal to S3 minus K, and that's the neighborhood of it, right? X tilde to be the infinite cyclic cover. And so x tilde is homotopy equivalent to just the cyclic surface. Right, because of fibering, right, we just tracked on the cyclic surface. And now, suppose there's a lower genus cyclic surface. So if there's this lower genus, let's see, okay, so H star of X tilde equals H1 and X tilde equals right? So if there's a lower genus cyclic surface, say sigma prime, genus G prime, less than G, well, then we're not going to get, this is not. First of all, what's easy is that any two fibrations have to have the same genus.
Because otherwise,
because any vibration gets used.
Yeah, right.
Okay. What's not quite so clear is that, so that tells us there's lower genus cyclic surface. It can't be a vibration, right? So we have something where we have, this lower genus surface, sigma prime, G prime, here, and then we have some critical points, right? Examples and so on. We get some higher genus surface, and so, put this together. You can help me out here. I want to say that. So there's. Let's see. It's escaping me.
this answers this is basically answers the question.
This answers even this part without.
Well, I mean, I guess a similar question is like, can you have vibrations of different genus?
Right. That's
so,
the thing.
I don't want to get too off.
Okay. So you think about that. I think it's not too far off from what we've done to figure this out. Well, okay. So what did I plan? My plan was to try to compute explicitly some S1 value Morse homology. Having battled with it over the weekend, I realized this is really not as I had some misconceptions and thought it'd be a little easier. So I'm definitely not going to be able to do the whole thing today. But what I want to do is at least sort of tell you, sort of let you see why it's kind of tricky, and try to set up most of what you would need to do and show you what you need to do to sort of finish the computation, right? Well, I mean, one thing, of course, that makes it tricky is that in computing the boundary map, in principle, you may have infinitely many, you've got infinite many powers of t that may show up, right? So right off the bat, that's something that should worry you. One hopes that in a particular example, you sort of see clearly what's going on and you can read off higher, you can read things off to higher order. But when working with homologies over rings that are not Z, typically you end up, if you really want to show for example, two modules over some funny rings are not isomorphic, that becomes a hard algebra problem in and of itself. Or even just to show that some module is not trivial, is not isomorphic to zero, for example. You've got some presentation for it, and it's a complicated algebra problem in and of itself. And so, that's why things like Alexander polynomial or there are lots of further algebraic invariants of modules over complicated rings that are developed precisely to deal with those algebraic problems. So there's sort of a second layer of invariance that comes up, and maybe what I should have done is just try to show you the Alexander polynomial. Maybe I should tell you right now without proving it. We were trying to. I wanted to do an example where I sort of show that a particular knot is not fibered. I won't be able to complete that, but I'll try and set it up. But I should tell you off the bat that there is a much easier way to prove a knot is not fibered. It doesn't always work, but which is that you can compute this thing called the Alexander polynomial, which arises from the homology of the cyclic cover. And you have to think about the presentation of the cyclic cover, get a certain matrix. It's got, everything's over, there's this module over, everything's over Z adjoint T. You've got polynomials, so then this matrix has T's in it, you take a determinant, that's a polynomial, and then it turns out that if that polynomial, if the thing's fibered, that polynomial has to be mnemonic. The leading coefficient has to be 1. So, fibered, this is fibered implies the Alexander polynomial is mnemonic. And the leading coefficient is 1. And so, very often you can prove things are not fibered by computing the Alexander polynomial, and there's very simple combinatorial ways to compute the Alexander polynomial. And you get 2, but of course that's not an if and only if.
Here you
go. So fibered implies, and the other direction is not true. And yes?
If the knot fails to be fibered, is it because it has it's a vibration with singularities, or are there other ways for it to not be fibered as well?
So it will always, the thing is you can always construct a circle value Morse function on the complement with in the homotopy class of the loop going around, so that the meridian to the knot, the linking circle to the knot, maps once around the circle. That's what's nailing down the homotopy class. Okay, and you can always construct such a map to the circle, and then but if it's fibered, that map will have no singularities, and in general you expect to have singularities. So what I wanted to do was to look at an example where we pick, we sort of see that it doesn't, we see some map to the circle, and it has some singularities. Of course, the fact that we see some singularities there doesn't tell us that there aren't, there's some other map that's on topic to it that doesn't have singularities. So then you would compute this homology, the circle by Morse homology, right, and show that it's not zero, and that would prove that it actually cannot. That would prove that you cannot homotop that map to get rid of the singularities. Right? So I wanted to sort of start that calculation and leave it. things have to end somewhere. Okay. So the knot I wanted to look at, well, so on Fridays, many of you weren't here, but what we did was we took a trefoil knot and tried to see that it was fibered, and then I tried to modify that, and then I got kind of hung up. But I at least can get past where I was hung up on Friday. So the trefoil knot can be thought of as sitting on a genus 2 surface as follows. Let me try to be consistent about colors. Let's try to use green for the knot throughout. I'll be erasing this picture a lot, so taking notes will be kind of a pain. You are taking notes. So this, I'm going to draw the trefoil knot as what's called a pretzel knot, which pretzel just means something that sits on this genus 2 surface in the following way. So it's just arcs at the bottom, and then as you go up along each column, you do some number of twists. Okay? So this is one way to draw the trefoil knot. And we were able to see that the trefoil knot fibers by basically seeing that on each, so the point is, this is, I've got a solid handle body here, solid genus 2 handle body, and the complement is also a solid genus 2 handle body. The complement has got these 2 pillars coming, it's got everything outside, and then these 2 pillars coming. Okay? And so, but you can also sort of think of that if you want, you know, sometimes it's useful to make one handle body when the other one contain infinity. If it helps, you can take this part of the handle body, make it bigger and bigger until it contains infinity, and then you see the complementary handle body is just a ball down here, handle going through there, and handle going through there. Okay. And so then we were able to see that both handle bodies actually are both handle bodies can be realized as a once punctured torus cross I in such a way that, so this handle body, so there's this handle body, let's call it A, this is 2 handle body, and then let's say B is a complement. And we were able to show that for K is a trefoil, which I've drawn, we can see that both A and B are diffeomorphic to sigma right across sigma -1, and that's also B, where sigma equals torus and one boundary component, and such that under both these diffeomorphisms, K goes to right this way, sigma across 0 on both sides. So K lies in the boundary of A and boundary of B. And so once you see that, then that's the point is you've got this vibration structure on either side, and you spin it around. Okay, so that was to show that the trefoil knot fibers. Another way to say that is that what we're doing is constructing a Circovite Morse function on the complement on S3 minus K by building it on A, by projecting it -1, 1, building on B, projecting it to, say, flip -1 was backwards, right? Take 2 copies of -1, 1, glue them together, make a circle, and then you've got this projection, which is a product on either side. Of course, the other non-trivial thing to figure out here is when you finally glue both sides together, there's some monodrome as you go around. That's tricky, but we'll see that we have to understand that. But I want to now complicate this picture, so another way to see it then is that on here I've got a surface, which is one, this green curve divides the boundary of this thing into 2 parts, and then I want to see that I can sort of push this red through this handle body and then out the other side, and it ends up being the complementary part of the boundary. Okay, so we want to see this solid handle body as a product of the red surface pushed through and coming out the other side. And that's not really too hard to see because you can really, if you like, you could just sort of, the point is because on this half it just goes straight through to the other side. this half that goes straight through from this side, and then as you're going through each of these pillars, it's just going through once, so it just, you know, if you push your finger in here, you come out here. And so that's not really that hard to see, but what I want to do now is complicate the picture so it sort of destroy that vibration structure by putting extra twists in the middle here. So I want to change this now. So now I put extra. So now it's I think this would be called a 1-3-1 pretzel knot. I don't care what knot this is. I'm just going to construct this somewhat at random to see what happens. And it's still going to be the case that inside A, we can still see. I just taken this thing, cut it open, put an extra twist in, and put it back. That's not going to change the fact that A is just got this nice product structure. It goes straight across. It's just got an extra twist in it. So I've got some sort of fibers pushing through A, pushing through from this, coming out the back, and they've just got an extra twist in there. But it's the complement where things are going to be screwed up. And that's where I got hung up last time. I think I can at least draw some kind of picture of what's going on in the complement. First of all, we could just look at the complement right there and be happy with what we have. But I'll try to make it a slightly different picture. I think I will copy that picture over here now, but try and improve it. I'm just going to try and make it look a little bit easier to work with. In particular, what I want is I want almost all of the green stuff to be in the front. That was what was hanging us up before. So the first thing I'm going to do is take, draw everything that will in front to begin with. What we need to understand is that this, everything that's going through those holes, I want to see what's going through those holes as something going over a handle in the complementary handle body. And so when this goes around the back and through here, instead what I want to do is I want to make it, right, so I want to pull this down. Actually, let me focus on the middle section here. This arc here, for example, goes around over. I want to think of that as going over this handle and coming back before it goes over this other handle. So there's a handle here and a handle here. So instead of going through and straight around the back, I'll do something that looks a little bit inefficient. Some space here.
Are you drawing the same course? Or
this is not the complement. This is the same solid handle body, right? I haven't gotten to drawing a picture of the complement yet. But I want to go straight, I want to go through and then straight. I just want to go straight through and over. And then I come up and I go over. And now I'm going to go back down again, right, in order to get back to here. Let me do this, through there, and I want to right away go down. Remember, green is just the worst of these colors in terms of staying with you a long time. And then something's going to come from here and go. And now they're going to all go back down again. Okay, so now this one is this top one here. It's got to go back down and appear at the top. And then come up. And then this one down here. And it's got to go and appear. So this thing, this is the middle one. Let's go straight across. Right, there's one I'm missing. Right? Tell me if I got it. Does that look right? Okay, so if I follow this, if I follow here, around and over. So instead I go here, down, up and over, and up. So that's resin from there to there. And then this one goes down, up and over and back up. That's to there. And this one goes down. And then I have to figure out what's happening on this other side, and again, I want this just goes straight over here, that's something exciting. And this one I want to make it sort of go all the way back here. So that's where I want to be. And something similar should happen here. I just want this to go. Okay, so the point is now I've really got everything in the front except for places where it goes straight through and back, right? And the sort of, I mean, it's not quite so obvious, but I've got things really divided down the middle, sort of, right? Stuff to the right, stuff to the left. So I want to try and draw a picture on the surface of the complementary handle body now. So I want to draw the complementary handle body a little bit more schematically than this. As so first of all, you might imagine, if you want, we can imagine that we've swallowed up and we've absorbed infinity into this handle body, so the handle body really is sort of all the way out there, goes out. And so I've got the complementary handle body is a ball down here, a handle going over, and a handle going over. But let's actually think of it as a ball in the front, and then a handle going through and a handle going through. So basically everything I've done in green that's not dotted is on the surface of the ball. And then I've got one handle attached that goes through here and comes back, right? And another one handle attached that goes through here and comes back. So really all I have to do is just copy this same picture, right? But let me draw it a little more. So I'm going to draw a surface. This is the surface of the zero handle body. And now now say that there's a handle attached which goes from here. Remember, let me do the handles. So there's a handle that goes like this, and a handle that goes like this. So that's this complementary handle body. And now I just have to copy this green curve exactly as I had over there. I said everything goes in, over. So then let me actually, well, yeah, I'll try to copy it exactly first. So if I look at this curve, it goes over the one handle and then pops out this side. And then continues. Here it's going all the way around and then over that one handle here. And then pop out the other side. And then it just goes over one handle, continues. And once it comes here, then it goes over and then it goes through this one handle. So it just goes straight across here. And it pops out here. So that's there. And now what does it do? It goes through that one handle again. So it goes to there. And then it comes through here and it pops out the other side. And it pops out. Remember, this is weird like that. So it should pop out over here. Let's hope that worked out right. Where are we here? Let's start again. There, went to there, over to here. So this point was there, over, and then over. I should mark where I'm going as I go. And then that's down to there. And now I've gotten here, which is, so let's see, what might you wonder? Why is, so there, that's right, it's over here now. What I guess is confusing is that this one handle goes over and pops down here, so it looks like it's attached. We look at these are sort of 4 points on the boundary of B, these are 4 points here, right? And they really are arranged in this way, lines up like that, so that's fine. We come here, we're in the second one over, and we come back over, okay, like that. It's here, we're up here, and now we again just sort of follow our nose. Everything is over, so we're really up here, or higher up than we were before. That's right. That's good. Something's wrong here.
Does it matter that it should be like mirrored?
No, it should be mirrored. So these points, 1, 2, 3,
No.
4.
I mean, like this picture and that picture, like shouldn't.
Whether
shouldn't
I've done
B-
something inside out.
Shouldn't B
Yeah.
be on our left and A be on our right?
Because you want to turn it around.
Yeah.
Um,
Or does that not? Is that not gonna
I
happen?
want to not. That's something I want to deliberately ignore. Okay, but let me number points along here, right? Because if we call this 1, 2, 3, 4, this is 1, 2, 3, 4. This is really the boundary. What's really going on is that this is the boundary A. So this is. I really should have started it this way as marking 4 points. 1, 2, 3, 4, and then marking 4 points here. 1, 2, 3, 4, and let's see if I got that right. So 4 should have connected to 4. That was the problem here. So let me do the same thing again here. I've got 4 points that I want to mark out as 1, 2, 3, 4. 1. Let's make this one green. 1, 2, 3, 4. 1, 2, 3, 4. And then mark them out here. 1, 2, 3, 4. Okay, now let's check again whether we got this right. So I wanted to start at, I came here, I went over 1, popped out here, and then this goes all the way around to 4. That's good. Pops out at 4. 4 is down here. I didn't mark these guys. 4, 3, 2, 1. Okay. So then I'm at 4, and now I connect over to this 4, pop out here, and that's where I should continue. Now 4 should connect over to 2. Okay. And now that's the mistake I made there as well. This doesn't go there. So then 4 comes to 2 there. And now 2 comes over, connects to 2. And now I'm here. 2, right, so that's 2 goes all the way around.
It goes around the
Back. All the way around and back to 1. Right? Now it's gone to 1, it connects up to here, to 1, and then it comes over to 3. Now it continues to 3, and then 3 goes over to 3 here, now it's coming out, and then we come here and we just connect. And then there's our number. Now you're right, there's something a little bit funny that perhaps I should have took a mirror image of the whole picture. But I think that I can give an approximately right picture without thinking about that.
But
So,
isn't that's just sort of where we are.
Yeah,
Yeah.
Like
we're
this-
just in the inside.
yeah,
Our perspective is different in that picture.
right.
And we don't
Let's-
have to worry about drawing the tubes between A and A because we've drawn the lines going straight, like vertical.
That's
So
right,
if we were to
yeah.
draw the tubes, it would just be,
That's right, so the tubes really, everything just goes boom, and it's parallel lines with the tubes. That's the convention I understand, right? And so now, again, let's remember where is our, so the point is here, our cipher surface is here. And we sort of nicely see that this thing can be thought of as that cipher surface cross interval. And that's a genus, it's still a genus 1 cipher surface with 1 boundary component. So that's in here, right? So now I want to transfer it onto this surface. So, for example, we can figure it all out by remembering that, for example, it goes through between. I already wish I'd done the other one.
2 and 3.
2 and 3 on A.
2 and 3, yeah. I wanted to do the other, so let's. Because I want it to be compact. I want it to wrap around the back right now. So let's suppose maybe the complementary one, just as good here. So I'm going to do this one instead. Sorry for the messy picture there, but anyway, you know what I'm doing here. So now the point is I want it to be this part. I think this connects to there. This connects there. Okay, and if you work it out, you can figure out that that's, again, a genus 1 surface. Now, here's the challenge. Now we have a handle body drawn schematically, a surface on its boundary, and I want to then think of this handle body as a cobordism from this orange surface to the complement of the orange surface. Cobordism with sides, but I'm suppressing the sides, right? Really, to do things properly, I should thicken up the green arc into a product, and then I want to see this thing as having corners, this surface is having corners along there. So I'm going from the orange into the, into the solid handle body, and then out to, I'm going to draw it to the black, right? And I want to see if I encounter any critical points there. So that may be the bulk of what we managed to do today, is just simply understand precisely a Morse function on this handle body such that the bottom level set is the orange surface and the top level set is the complementary part of the surface, right? And again, remember, if you wanted to, this is all in the not complement, so that's why we have sides to our cobordism. So schematically, we have, sort of want to think of this thing as this. This is the orange on the bottom. And the green up here, really. But it sort of extended the orange all the way up the sides. If we did zero surgery on this knot to work with a closed three manifold, that would make this a closed surface, and then we wouldn't have to worry about the boundary, but then it's a little hard to visualize what's going on. So we want to sort of see what happens as we sort of start sweeping out across this cobordism to get to the top, and do we get some other, whatever it is, we get to the top, and do we encounter any critical points as we go, or is it a product? And so now what I want to do is say, okay, let's look at this one hand, what goes up here, and see if we can, when we were working with the trefoil and its complement, see what happened here is if I slice across this handle body, the green curve intersects it twice, okay? But now when I slice across this handle body, the green curve intersects it 4 times. So that's not, when the green curve intersects that cross section just twice, then I can sort of, push the orange surface through to the other side smoothly. But here I can't, if I try to, well, I'm going to draw a picture now of what a cross-sectional slice of this one handle looks like, and we see that we're sort of forced to have a index 1 critical point inside each one of those. So let me tell you what I claim. I claim that there's a natural handle decomposition of this handle body with two one handles and two handles. Okay, that realizes that this handle body has a cobordism from this orange genus 1 surface to the complementary genus 1 surface. I want to take, let's say, the one handle A, and I want to draw it sort of all by itself. And it's attached. I'll draw the rest of the stuff that it's attached to. Okay, so this is a big zoomed in patch of this disc here, and on the right is a big zoomed in patch of the other disc. And I want to draw the green arcs going over it. So I just got 4 of them. But how do I want to do this? I want to do yeah, I was trying to decide whether to try and put everything in the front or to try and draw them symmetrically spaced. Try to work like this. I was trying to decide whether to sort of put something more realistically in the background. So, you know, this I clearly don't have locally a product structure, right? I clearly don't have these two orange strips across I. I have something more complicated. So, how do you see what you have? Well, I want to say that inside here, there's a one handle.
Can you label the intersections like 1, 2, 3, 4?
Yeah, okay, that's fine.
And they go across the same.
If anybody in this audience is careful about a picture like this, it should be
Which, and this is directly related to what I need, so I'm trying to keep.
So suppose you take let's see this. Let me zoom in on a cross. So this is a cross section. And there I see. Now this is where I'm going to displace them a little more evenly. And here's orange, right? And then you can sort of see quite clearly that if I try to let me actually be careful about the corners now. Well, I can take that cross section, right, and I can actually draw it a little bit more Cobordism-like, right, by making it, let me make it a octagon. I'm going to put the green stuff here, and the orange stuff here. And then you can sort of see there's this natural foliation of it, or map, there's this same old picture we've always drawn, right? And then you see very naturally that a cross section just has a two-dimensional cobordism. There's a cobordism from the orange to the white, right? And your next one critical point in the middle, right? But if you thicken it up a little bit, it's the same thing. We still have index one critical point. So if I'll try to hazard a drawing that's a three-dimensional drawing.
So you thicken it up, so you still have index 1, it's just now it's a index 1
Now it's a
critical point and a
three-dimensional index one
three-dimensional.
critical point, exactly. Something like that, and this is now the orange stuff up the top. There's the orange thing, and then the green arc is going across here. Right? And there's a three-dimensional cobordism going from there to the complement. Okay? So, but really all you've done in the end is, if you want to think about what the cobordism is, you take a little, you push the orange stuff in a little bit, and then you connect them by a sort of tube in the middle. And that's really all you've done, because this is just a one handle. It's an index one critical point connecting, attached there and there. So another way to say it is that what I've done is I've got this pre-existing three manifold, and I'm trying to decompose it into handles. Okay, so I start on some part of the boundary, and first I just push everything in a little bit to get a product, right? And then I'm going to attach a one handle that goes straight through there. So this is going to seem funny. It's like one thing you can do is say, well, okay, I'm going to take this three-dimensional cobordism apart, piece by piece. I'm going to just remove all the stuff. So the first thing I'm going to do is I'm going to realize that there's a one handle in there that goes straight across there. So let me just drill it out. Okay? And so I've attached the one handle, and I've changed lots of things here. In particular, so I want to understand now, so I've attached this one handle, but now let me sort of make it fatter, right? Sort of, let's proceed along a product, right? So if you, let's see if we can do this. Suppose you take a one handle like this and you drill a hole through it. And now you start, so what has happened to, I want to sort of see the new boundary after this, as much as possible in this picture, okay? So the first thing that will happen is that I'm going to expand, sort of cut a hole out on all the way across from right there, and same thing. So I can make that long and thin, right? This thing that I attached it on, okay? And so where does that pop out here? There's a, I want to say that I'm attaching it, I'm drilling out a one handle. Right there, and okay, so once you've done that, the claim is that, do everyone agree that this, so I've sort of got two discs here, along which where this one handle is drilled out, and if I expand it so that I see those discs over here, they pop out as two sort of little earlobes there, right? Okay, now let's try to enlarge things a little bit more, and the point is now between 2 and 3, for example, I've got this bit of orange surface that goes up and over, it comes back, and I can just, there's a sort of a strip here that goes up and over, and the point is now I can what I want to do is this. Let's see, this is what made sense to me earlier. I want to say that in the end I've done this, and I have
You've done like a handle slide or something.
yeah. So let me better justification of this earlier. Okay, maybe since we're running out of time, let me ask you to trust me that you can do this process, and you can see that there's by passing through an index 1 critical point, okay, you can get to the point where I now have everything on a I'll have let me redraw this picture a little more carefully, and
You like slid the knot off that one handle?
yeah, that's sort of what I've done, and so I want to see this. I should have a higher genus surface now because I've passed through and I've attached. So I should go from it being a genus to a genus 1 surface, and I've attached to a genus 3 surface. Okay. Let me even short circuit even further and go to Let me go back to the original picture and show what I really want to do is sort of so that we can actually draw this. I still have it over there. So let me go back to this picture and sort of think about what we did. What I claim that we did is that we found inside here, where's my orange? This was our, so it's here. So, etc. So in the end, what we do essentially is we say, now we can actually see it working in the complement, right? So let me drill out a one handle from the complement. Exactly what the point is, we drilled it. Here's the one handle that we drilled through. So another way to say it is we just changed this original surface. There's our one handle. Okay. And similarly, I should do it something here. Here's our. Okay, so now what you really want to do is remember that when you're doing Hagar diagrams of three manifolds, what you really want to do is work in the middle level, which is the highest genus surface, and draw the attaching curves for the two handles above and below. So what this analysis, which I should have gone much quicker through, shows us is that we have another cipher surface, which is a genus 3 cipher surface for this knot, which is just the original orange cipher surface with some extra genus added that kind of looks like dumb extra, worthless extra genus. But it will have the property that now I can see, the point is now I can see that to undo this attaching of a one handle, I can attach a two handle along this curve here. And so I have this orange cipher surface, which includes all of that, but I can decrease the genus in one way by attaching two handles along those curves. That gets to the lower genus cipher surface. And what I want to see is that there's another way to decrease the genus on the other side. So I want to see this complement is built by actually starting with the genus 3 cipher surface. On one side, attaching two handles along red curves. On the other side, attaching two handles along some different curves. And then both sides will get down to a genus 1 cipher surface, which then the last thing you have to do is figure out the monitor, the gluing math there. So the picture is going to be, we'll have a circle by a Morse function. We'd have our genus 3 cipher surface here, our genus 1 cipher surface here. We'd have two critical points. So they would be index 2 going this way, index 2 going this way, and I want to draw on that surface, which is still in surface embedded in R3. I want to draw sort of two curves for these and two curves for those. Okay. And so I will hazard, no, I won't hazard drawing again. The other curves then end up being, if I did my computations correctly, one of them goes around, over, and around like that. And you can sort of see that will cap off. I mean, well, actually, the first thing that's clear is that bounds a disk in the complement. No problem, right? So, it also, I mean, I could have, if I didn't care about the knot and just wanted to build S3, I could just as well close it off there. But I wanted to draw this blue curve that lies in that surface the whole time. And now I need to draw another blue curve that lies in the surface that also bounds a disk in the complement. So once I can cap that off and bound a disk, and then I need to do another curve, and that one goes, I believe, both of them go over both of these red curves, right? So one will go here, comes there, comes on that side, over, and it goes over the back there, and it comes here. So essentially what I've done is I've drawn an embedded surface in R3, which is obviously not genus minimizing, because I can find four different simple closed curves on that surface, which bound disks in the complement. But the fact that it's obviously not genus minimizing in these different ways is really showing us the handle decomposition of the complement, right? So I draw this surface. I see that and the other thing that's important is that the disks are on different sides. So the red curves bound disks on one side of this surface. Right? The blue curves bound disks on the other side, right? And then sergering. So then, what's much harder to see, right? Well, it's not so hard to see what happens when you then serger along those red curves, because that's just cutting those. What's hard to see is when you serge along the blue curves. you'd have to isotope the surface around until those blue curves sort of, you naturally see the disks that they bound, right, which are kind of big, right? And so you have to draw the surface, you know, isotope it around until it bounds a small disk, pinch it, cut it off, and see that surface. And then finally what you have to do, you have to see how that surface, how the two surfaces you get, pinching the red curves going in, pinching the blue curves going out, end up being isotopic to each other. So then you can find a gluing map, but that isotopy, what the final step you need to do, and now we don't have time, is draw on each of those surfaces, the genus 3 surface, you want to understand how one is glued to the other. How do you figure out how one surface is glued to the other? What you should do is draw arcs that cut the surface up into disks, into a disk. So if you have a genus 2 surface, you can draw a collection of arcs and cut it up into a disk, and you see how those arcs, how the one set of arcs relates to the other set of arcs, and that will determine the gluing map up to isotopy. Finally, so if we look at just a little bit of this, you know, we see a tiny bit of the Morse homology here, because the Morse homology would be generated by this is index 2 going that way, so say index 1 going that way. So we have two things of index 1 and two things of index 2, right? And so, you know, C1 would be generated by A and B, and C2 would be generated by C and D. And we would know that the boundary of each C was well, it's going to go forwards and backwards. That's the critical thing here. It's going to go over, oh, I'm sorry, the boundary of each C is A plus, boundary of C is going to be A plus D plus B. Well, that's at the first level, plus higher order terms, right? Because we don't know the monodrome that goes around. And then the boundary of D will be A plus B as well, because it hits both of them, right? And plus higher order terms. And the higher order terms, of course, are what? Not completely shoved in the rug. And that's where, you know, if you just knew it was this, then you know the homology was not zero. Okay? Because their boundaries the same thing, right? So they, the difference of them would be, for example, you'd have a non-trivial zero site, right? But, you know, because T is as good as 1 in homology, you have to be stuck. But we are sadly out of time, so thank you for your patience.
So then the condition, the conclusion you would draw is if you're able to show that this was non-trivial, then it's not.
And it's not fiber. And there are easier ways to do that.